So, hello friends. In the last video, we have seen the digital communication, especially the pulse code modulation. We have seen that the like continuous time signal MT is converted into samples, and this samples is further quantized and then encoded, and then we are left with bits or stream of bits. Now, these bits can be transmitted in two ways. One, directly through wired communication, or other through free space. This is what we have started the last video. So the wired communication part, this part that is related to PCM, we have done. Now for the free space, we have modulation techniques. We have modulation techniques that we will do in this video. So like these are the bits. Suppose up to this part, up to encoder, we have understood. And how this encoder or bits are being transmitted through PCM, we have understood. Now let us assume that this is the bits, these are the bits, okay, for the samples that are quantized and encoded. These are the bits. Now these bits need to be transmitted through free space. When these bits will be transmitted into free space, obviously we will need a modulation, and different types of modulation technique are amplitude. In analog we have what? Amplitude modulation, pulse modulation, frequency modulation. Here we have amplitude shift keying, phase shift keying, and frequency shift keying. FSK, ASK, and PSK. Okay, this is the three technique that we will go to, like we will understand in this video. So if we are using bit by bit transmission, bit by bit transmission. In the previous video, we are aware of TB. What is TB? Which is the bit duration. We are aware of it. So here, if we are going for bit by bit transmission, that is, you transmit this bit, then you transmit this bit, then you transmit this one bit, then you transmit this zero bit. So how many different types of signals you are going to require? You are only going to require two different signals. Two different signals. Why two different signals? Because for single bits means n equal to 1, how many different signals is required? That is 2 raised to the power n, that is equal to 1, that is 2 raised to the power 1, that is equal to 2. Okay, only two signals are required to represent these two bits. So here, if we are doing bit by bit transmission, that means either we will have to transmit 1 or we will have to transmit 0. So there is only two different bits that is going to be transmitted, 1 or 0, and therefore we only require two different signals. Okay, so therefore this scheme is known as, when we do bit by bit transmission, the scheme is known as binary signaling scheme. This scheme is known as binary signaling schemes. Okay, so we have to only find out the ways how we can represent bit 1 and we can represent bit 0. So if suppose we find any signal S1T which is representing bit 1 and any signal S2T which is representing bit 0, then if we want to transmit 1011, we are going to basically transmit S1T, S2T, then again S1T and S1T. These are the signals we are going to transmit it in free space. Okay. So now let us start with the amplitude shift keying, ASK. In amplitude shift keying, one is basically represented by the presence of a carrier, AC cos 2 by FCT. This is the bit 1. So suppose if this is the bit 1 represented like this, say this is 5 volt. So this will be like TB, and this will be represented by the presence of carrier. Okay. Now another 0 bit, if this is 0, so there will be no carrier. Again, if there is carrier, means again you are transmitting 1. Okay. So In amplitude shift keying, what we are doing, we are representing 1 with the presence of carrier, that is AC cos 2 pi FCT, and 0, we are using it that the amplitude is 0. Put AC is equal to 0. Or we can say that the absence of carrier, no carrier is being transmitted. Now, in the like analog modulation techniques, we have seen that AC cos 2 pi FCT and power of the carrier is given by nothing but AC square by 2R. And if R is taken as the unit resistance, then power is given by AC square by 2. But since here we have the limited signal, it is only up to TB. So here we define energy, and energy is nothing but power into time. So here energy of this signal, let us represent this signal as S2T and this signal as S1T. Let us 0 be represented by S1T, that means no signal is there, absence of carrier. And ST2 is represented by AC cos 2 pi FCT, that is carrier is there. We are basically multiplying the carrier with 1 and 0. So energy is given by energy is equal to power into time, that is AC square by 2, AC square by 2 into TB. This is EB, energy per bit. The energy of 1 bit is given by AC square by 2 into TB. This is important and you should remember this. Okay, now what is the carrier? Carrier is given by AC cos 2 pi FCT, and we have EB as AC square by 2 into TB. From here we can get AC as AC square as 2 EB upon TB, or AC can be given as root over 2 EB upon TB. This is AC. We are trying to represent amplitude in terms of the energy. Why we are doing this? So that the signal could be easily represented in the constellation diagram. Constellation diagram. What is constellation diagram? In which the axis represents the energy of the signal. Okay. Sorry. So if this is clear with you, so in case of ASK, what we are having? We are having, this is binary signal scheme, binary signaling. So we will always be going to talk about only two different bits, that is 0 and 1, or we can say two different signals, that is S1T and S2T representing 0 and 1. So 0 we have already seen is represented as AC cos 2 pi FCT multiplied by 0, that is nothing but 0, and 1 is represented as AC cos 2 pi FCT. Okay, and also here we have seen that AC can be represented as root over 2 in root over 2 EB by TB into cos 2 by FCT. So if we make the constellation diagram of this is 0 and this is nothing but EB, energy bit, energy per bit, or energy of the bit, 1 bit. So if this point, suppose if this point is my root over EB, if this point is root over EB and this axis is given as like 2 by TB, the axis of this axis is represented as 2 upon TB. 2 upon TB. So if you see that if the axis is represented as root over 2 upon TB, then what we are left with? Root over EB. So if this point is root over EB, so this point is 0, then we can say that if we want to represent this signal, let's say suppose this is S1T and this is S2T. So if we say that this is nothing but 2 by TB cos 2 pi FCT, if this unit is representing, or this axis is basically representing this thing, each measurement on this axis, each measurement on this axis is basically what? It is root over 2 upon TB into cos 2 pi FCT. So if this is 1, so this basically represent 1 into 2 root over TB cos 2 pi FCT. If this is 2, it is going to represent what? 2 into root over 2 upon TB cos 2 pi FCT. So this point, if this point is EB, if this point is EB, so if this point is like root over EB, then we can say that at this point represent nothing but S1T. Okay, because if this point is the root over EB, then this point represent what? Root over EB into root over 2 upon TB cos 2 pi FCT, which is nothing but S1T. So S1T can be represented as this, and the distance from the origin can be given as what? Root over EB. And this is nothing but S2T, which is 0. Okay. If this is understood, then what is the D minimum? What is D minimum? D minimum is nothing but the minimum distance between these two signals. So what is it? It is root over EB. This is D minimum. And then we have understood probability of error. Probability of error, P of A is nothing but 1 upon D minimum. These two formulas are very important, just remember. Also, if we see what was the energy of S1T, sorry, S2T, energy of S2T was nothing but what we have figured out here. It is EB. Energy of S1T is nothing but EB, which is given as energy of S2T is nothing but EB, which is given as AC square by 2 into EB. Okay. So here in this constellation diagram, the distance of S1T from origin, it is root over EB. So if this distance is D, so we can say that distance whole square is nothing but EB. Distance whole square is nothing but EB. So the distance of any signal from the origin gives the energy of that signal in the constellation diagram. Just remember, distance of signal from origin in this constellation diagram, where one of the axis represent root over 2 by TB cos 2 by FCT. So it gives what? Energy. Distance square, basically, not distance square of the signal from the origin is equal to energy of the signal. Okay. So if this is understood, so we can summarize here for ASK, amplitude shift king, what we have? We have bandwidth is equal to twice of RB. In the AM we have twice of FM. Here we have twice of RB. What is RB? RB is the bit rate. RB is nothing but 1 upon TB, this bit rate. Okay. D minimum, this is formula number 1. D minimum is given by root over EB. D minimum is what? Is the minimum distance between S1 and S2. Minimum distance between S1T and S2T. Between two signal. Any two signal. But here there are only two signal S1T and S2T. Therefore D minimum is distance between them. Probability of error is nothing but 1 upon D minimum. We have understood. And fourth point is, it is distance between this signal and the origin. Square of that is nothing but the energy of the signal. Okay. Now let us move to phase shift keying. See, again we have to represent only two signals, 0 and 1. So in phase shift keying, this is, if this is like our carrier, so we have to modify its phase. So total phase is what? 360 degree. For two signals, how many phase difference we required? That is 180 degree phase difference is what we required. So if one signal is given as a phase 0, if one signal is given as a phase 0, another signal can be given as phase what? pi. Another signal can be given as phase pi. So if this is phase 0, this could be written as AC cos 2 pi FCT, and this could be written as AC cos 2 pi FCT with a minus sign. Okay, cos 180 degree plus theta is nothing but minus cos of theta. Using this formula, this 180 degree plus pi can be written as this. So here in PSK, what we have? In PSK, we have S1T is given as simple carrier AC cos 2 pi FCT, and ST2 is given as what? Negative of the carrier AC cos 2 pi FCT. So just remember, in the case of AM, we have for demodulation, just remember for demodulation, we can use the envelope detector as well as the coherent detector. कोहेरेंट डिटेक्टर क्या है? वो सिंक्रोनस डिटेक्टर जो हम लोगों ने एएम के टाइम पे पढ़ा था, वो ये दोनों यूज कर सकते हैं, ठीक है. एंड दिस डिमॉड्यूलेशन इज व्हेन वी यूज कोहेरेंट डिटेक्टर, क्वाड्रेचर नल इफेक्ट इज पॉसिबल इन एएसके. क्वाड्रेचर नल इफेक्ट इज पॉसिबल इन एएसके. Similarly for PSK, so this is S12, S1T, S2T. So if we want to draw it in the constellation diagram, and this is given as 2 by TB cos 2 pi FCT. So this value can be given as EB, and this value can be given as minus of EB, as this can be represented, AC can be represented in the form of EB. From here, we have this equation between AC and EB. So if you rearrange AC in terms of this, so what you can write? This can be written as root over EB into 2 upon TB. This is AC into cos 2 pi FCT. So if we plot this, so what we will get here? Only root over EB, and for here we will have minus root over EB. So what is the minimum distance between these two signals? This is the minimum distance, D minimum. So what is D minimum over here? So D minimum here is nothing but 2 root over EB. Okay, what is the distance? This is 2 root over EB. So this is D minimum in case of PSK. And probability of error will be equal to 1 upon D minimum. मतलब कि जितना ज्यादा डी मिनिमम जितना बड़ा होगा, प्रोबेबिलिटी ऑफ एरर उतनी कम होगी, उतना कम एरर होगा. ऑब्वियसली बात है ना कि if two signals are wider apart, then their chances of error is less. So what is the energy of the signal? This is the distance of the signal from the origin, that is EB, root over EB, and this is also root over EB. The energy is given as the distance from the origin whole square, that is EB whole square, EB whole square, root over EB whole square, which is nothing but equal to EB. Okay, that is obvious. That is energy is EB only. From here only, from this assumption only, energy EB is given us all this thing. We are proceeding forward in this constellation diagram. So basically energy is EB, and this is also equal to the distance from the origin of the signal. That is to be remembered. This is the point that is to be remembered, the distance of signal from origin. Okay, easily. So for demodulation, I'm only discussing the important point. Okay. For demodulation of PSK, like angle modulation को हम लोग क्या ED के through demodulate कर पाते थे, नहीं कर पाते थे unless we use a differentiator. So here also demodulation envelope detector is not used. It is not possible to demodulate an PSK with an envelope detector. Second point, so what we are going to use? We are going to use the coherent or synchronous detector. Synchronous detector. So is it affected by quadrature null effect? Yes, it is affected by quadrature null effect. ASK is also affected by quadrature null effect, and this is also affected by quadrature null effect. Okay. Now bandwidth. What could be the bandwidth? So bandwidth will be equal to about the bandwidth of the PSK. So bandwidth of the PSK is same as the bandwidth of the ASK. which is equal to twice of RP. Okay. So now we are left with FSK. In FSK also same. We'll have to represent 0 and 1. So 0 we can represent with the carrier frequency here. In FSK, what we have to modify the frequency of the carrier. This is the carrier. Like in PSK, what we have done, we have modified phi. That is the phase. That is AC cos 2 pi FCT plus a phase. So this phase is modified. For 0, we take it at 0. For 1, we take it as pi. Okay. Or whatever you want to take. But the phase, it has to be modified. In FSK, they are dealing with frequency. So like for 0 can be represented with some lower frequency and 1 can be represented with higher frequency. So here we will be using two frequency. One is the lower frequency and one is the higher frequency. Okay. So let this be S1T, signal S1T. So S1T can be given as AC cos 2 pi FLT, and signal S2T can be given as AC cos 2 pi FHT. Okay. Now for like demodulation of FSK, for demodulation of FSK, now some important point with respect to FSK. Note down some important point with respect to FSK. Number one, we use NRZ coding. In FSK, what we use? NRZ coding. Number two, to represent this S1T and S2T on the constellation diagram, S1T and S2T must be orthogonal. Must be orthogonal. Okay. So to maintain orthogonality, what we have, FH minus FL must be equal to NRB. That is the condition to maintain the orthogonality. What do you mean by the orthogonal signals? If S1T and S2T are orthogonal, that means if they multiply, the product would be 0. If S1T is orthogonal, so is multiplying itself with give the S1T only, the signal itself. When, however, when this will multiply with one another, the output will be 0. So such signals are called the orthogonal signals. So if we are using the like coherent detector, if we are using the coherent demodulation or modulation. So for coherent modulation or coherent demodulation, whenever the term coherent is used, just remember to maintain the orthogonality, we have FH minus FL is equal to NRB by 2. Okay, FH minus FL is NRB by 2. This is an important formula that you have to remember. And when nothing is mentioned, that is coherent or non-coherent is not mentioned, just remember that FH minus FL is NRB. N is number of bit. In this case, we have 2. ठीक है? So S1T and S2T को constellation diagram में we will represent. For that, we have to maintain orthogonality. And orthogonality, this is the condition for coherent and non-coherent, or if nothing is mentioned, this is the condition for coherent, this is the condition. Correct? This is 2 points. First point, NRZ coding is using, and this orthogonality. What about the bandwidth? So bandwidth is given as what? FH minus FL plus twice of RB. This is the bandwidth. This also you remember. See, like I am only discussing the important points that is very important from this point of the point of view of examination. Okay. So now let me compare this. Let me compare this. Comparing ASK, PSK, and FSK. Suppose this is ASK, this is PSK, and here we have FSK. So in what about the bandwidth? So bandwidth we are having twice of RB. Bandwidth we are having twice of RB. So bandwidth we are having twice of RB plus FH minus FL. Okay, this is the bandwidth. Second parameter, what is D minimum? Minimum distance between two signal. In case of ASK, we are having root over EB. Here we are having 2 root over EB. And here we are, what we are having? It will be equal to like 2 EB. Okay. Why? Because why? Because why? Because we are going to represent one signal. This is S1T and this is S2T. This is I'm asking for FSK. So this is basically the D minimum. That is equal to 2 root over EB. Okay. So now, now you see, like we can say that the bandwidth of ASK is equal to bandwidth of PSK, but both these bandwidth are lesser than the bandwidth of FSK. That means the bandwidth of FSK is highest. First comparison. Second, C. D minimum is highest in number one PSK, then it is for FSK and lowest in ASK. So probability of error is what? It is inversely proportional to D minimum. So probability of error will be more where D minimum is less. So D minimum is less is where? In ASK. So probability of error in ASK will be the highest, followed by probability of error in FSK, followed by the probability of error in PSK. So which should be most favorable? So this PSK is most favorable to be used. Why? Because we have the least probability of error and the least bandwidth. Though bandwidth for ASK is equal to PSK, but we are also getting the probability of error the least. So a PSK is used. PSK is generally used. Also, in PSK, we cannot demodulate using ED, so we use the coherent detector. Here, demodulation with ED is possible, with coherent detector is possible, and also in FSK, as in the case of FM, we have both ED and coherent detector can be used for demodulation. But only in PSK, ED cannot be used. This is like affected by quadrature null effect. That is QNE is possible here. We have seen what is QNE. QNE is also possible here. We have seen this also. So this is what we have with respect to the binary signal scale. This is all with respect to the binary signaling. Now let us move to M-array signaling. M-array signaling. Suppose M-array signaling, what we do? We groups the bits. We groups the bit into one, like suppose we take this 2 bit and we arrange this into an array of one symbol. Array of one symbol. Okay. So for M-array signaling, how many symbols are there? M symbols. Okay, remember that point. If M array is signaling, there is total number of symbols is M. In bit by bit transmission, what we were doing, we were transmitting each bit. Okay, but here what we will do, we will group the bits into one symbol. We will group the bits into one symbols. Okay, into one symbols. And now, instead of transmitting bits, we will transmit this symbol. This symbol will be transmitted. So if there are M symbols, then we can say that the total number of bits required to represent these M symbols will be nothing but log base 2 M. Okay. say for n number of bits, we can represent 2 raised to the power n symbols. Okay. So if we want to represent m symbols, what number of bit is required? So if we take log both sides, we will get n log base 2, 2 is equal to log base 2 symbols. This log 2 base log 2 width of 2 is 1. So n is nothing but log base 2 and m, where n is number of symbols that we are basically transmitting. So if m as signaling is used, so number of bits will be log base 2m. Now this is very important. For example, if we take n equal to, for example, 2. Suppose if we are taking n equal to 2, so total m will be equal to 4. That means 4 symbols. We can transmit 4 symbols, and to represent 4 symbols, we will use log base to 4 4 bits, that is equal to 2 bits. Okay. If this much is clear, this much is clear. If this much is clear, so suppose this is my symbol M1. If this is representing with 2 bits, this 2 is 2. So this will be 1 bit, this will be 2 bit. So what would be the energy of M1? It will be nothing but 2 into energy of EB. Or we can say that the energy of this symbol S, ES, energy of this symbol S is nothing but energy of bit multiplied by log base 2 M, where M basically represent what is the total number of symbols that we are transmitting. For 4, m equal to 4, we are obviously getting 2 only. So this is the formula which you should remember for symbol. What is symbol? We have understood. Group of bits is arranged in one array, which is known as symbol, and these symbols are being transmitted. So energy of the symbol is given by EB into log base 2m. What is D minimum? D minimum will depend upon the cases, from case to case, but energy is this. What would be the bandwidth? Bandwidth. Now the bandwidth will obviously decrease, and it will be given as like 2 RB, or basically bandwidth of like if ASK, FSK or PSK, whatever bandwidth you are taking, it is going to reduce by log base 2m. Generally for ASK and PSK, what do we have? 2 RB. So it is going to reduce by base log 2m. This is the reduction in the bandwidth. Just remember. Okay. When we will do the numericals, these things will get more clear. Now, this bandwidth we are assuming when we are sending, remember, when we are sending the rectangular pulse. In the case of PCM, we have seen that the bandwidth is given as RB, which is equal to NFS. In the case of PCM, if you will see the previous video, you will understand that. So in case of cosine, raised cosine pulse, we have 1 upon alpha by 2 is the multiplying factor for the bandwidth, where alpha is equal to 0 represent the sync pulse and alpha is equal to 1 represent the rectangular pulse. So in the same fashion, if we are assuming the rectangular pulse, that is okay. But if you are using the raised cosine pulse, this bandwidth will be multiplied by 2 RB by log base 2m. This will be multiplied by a factor 1 plus alpha by 2. So this 2 and 2 will be cancelled out. So bandwidth will now become RB into 1 plus alpha upon log base 2m. This is for raised cosine pulse. Bandwidth for raised cosine pulse. Raised cosine pulse. Okay. Now this scheme. So this is also known as the binary phase shift keying, BPSK. Both are same. Okay. Binary phase shift keying means only we are using 2 signals. Now if we come to the M array PSK, where we are now not transmitting bits, but we are transmitting symbols. So, okay, before going into M array PSK, let us understand what is the symbol rate, what is baud rate, what is bit rate. See, there is a relation. Symbol rate is also known as the baud rate is equal to baud rate, and this both is equal to like bit rate upon log base 2m. So if we say B, if this is the baud rate, so B can be given as RB by log base 2m. Okay, this is not bandwidth, but it is the baud rate, and RB is the bit rate. Okay, and M is nothing but number of symbols. So this relation you understand. So when we say the symbol rate or the baud rate, it means the bit rate by log base 2m. Now in case we are representing binary phase shift keying, binary PSK or binary ASK, then M what is what? M is only 2. So if we put M equal to 2, what we get? Bit rate is equal to baud rate is equal to symbol rate. B is equal to RB as log base 2 M is 1. So for M is equal to 2, when we are only seeing two singles, in that case we say we are representing two different bits, which each bit has a unique signal. So for that case, we have bit rate equal to baud rate. And for M array, we have bit rate, baud rate is equal to bit rate upon log base 2a. Now come back to M array PSK. So here what we are having, like for M array PSK, we are having how many symbols? M symbols. Okay. Now see, in M symbols, we have understood bandwidth. What will be the bandwidth? Bandwidth will be 2RB upon log base 2. Why I'm specifically discussing the M array PSK? Because most of the question come from PSK only. Okay. So this is the bandwidth that we have already seen. What is energy? ES is equal to, what would be the energy? ES is equal to log base 2m multiplied by EB, energy of the signal. Number 3, D minimum is, what is D minimum? D minimum is nothing but 2 into root over EB, that is the D minimum of one signal multiplied by sine pi by m. Okay, this is the D minimum. So what is D minimum? So what is D minimum? D minimum is nothing but 2 root over ES into sine pi by m. Very important formula, remember this. So why here we are having ES? Just remember, this is ES, not EB. It is not EB. In case of PSK, what we are having? In case of PSK, D minimum is given as 2 root over EB. Okay. PSK में 2 root over EB है. But here for M array we are having D minimum in terms of E symbol. 2 root over ES into sine pi by M. Although if you will expand this, you will get the same point also. For D minimum for M equal to 2, that is called as binary phase shift king or phase shift king, what we will have? 2 root over ES into sine pi by 2. Sine pi by 2 is nothing but 1. So we will have 2 root over ES. And for what is the ES for PSK? ES is equal to EB. When we are talking about PSK, ES is equal to EB. Why? ES की general formula क्या होता है? Log base 2m into EB. And for m equal to 2, if m is equal to 2, so log base 2m, this is 1 only. So ES will become equal to EB. So this PSK के लिए, this will become equal to what? D minimum for PSK will be equal to what? 2 root over EB, that we have also seen above. So now when we talk about the QPSK, quadrature phase shift king, obviously we are meaning that m equal to 4, and 4 symbols are being transmitted. So in the case of m, you put here 4, here 4, here 4. So let us calculate d minimum. So d minimum will be equal to what? 2 root over es into sine pi by 4. The value of sine pi by 4 is nothing but 1 upon root 2. This is 2, and root over es is what? Es is nothing but, what is es? Es is this. That means log base 2 into 2. For m equal to 4, log base 2, 4 into EB. So this is 2 EB. So here we will have what? 2 EB. So this root 2, this 1 upon root 2, and this root 2 will cancel out. So we are left with 2 root over EB. This is the D minimum of QPSK, quadrature phase shift key, is nothing but 2 root over EB. Now you see that D minimum of QPSK and D minimum of PSK are same. That means what? Probability of error for PSK is equal to probability of error for DPSK, sorry, QPSK, quadrature phase shift king, which is equal to what? 1 upon D minimum, which is equal to what? 1 upon 2 root over EB. Got it? Okay, done. So now, again, we have done with this M array signaling. We have seen the means the formulas for the QPSK. Now we have seen that QPSK demodulation is affected, or PSK modulation is affected by quadrature null effect. To overcome, we use another technique which is known as differential phase shift keying, DPSK. Okay, so why we use DPSK? Just to avoid the quadrature null effect, which is one of the drawback of PSK modulation using covariant detector. So in DPSK, what we do? In DPSK, what we do? Before giving it to the like the PSK modulator, we have a differential circuit. Differential circuit. What this do? This is basically what XNOR gate. Before you give the bits to the PSK modulator, you just give it to the XNOR gate, which is a differential circuit, and what output is generated, you give it to the PSK. Okay. So, like, you write one question to understand this PSK. Sorry, DPSK. That a binary sequence like 1001 is transmitted using DPSK modulation technique, and given as the reference bit is given as 0. Find the phase sequence. क्या फाइंड करना है? फेस सीक्वेंस. फेस सीक्वेंस फाइंड करना है. तो XNOR गेट की प्रॉपर्टी क्या होती है? XNOR गेट, दिस इज द XNOR गेट, दिस इज A, दिस इज B. XNOR गेट की प्रॉपर्टी क्या होती है भाई? A बार B बार प्लस AB. That is what it will do. It will act if you give 1 as an input. Suppose if you give A as 1, we put A as 1, we will have 1 B bar plus, sorry, A bar will be 0 into 1 into B. So this term will cancel out. So output will be what? B. So if 1 is given, it will act as a buffer. Suppose if 0 is given, take A equal to 0. So this will be A bar will be 1, B bar plus A is 0 into B. So this term cancel out, B bar. That means if 1 is given, it will act as a buffer. If 0 is given, it will act as an inverter. This thing we will do in electronics, digital electronics. Okay, so now if this is the sequence and it is said that the reference bit is 0, that means the reference bit is 0. So if 1 is given, like if 1 is given, so what will be the output? At 1 it is acting as a buffer, so reference bit will be the output only. Next time 0 come, at 0 what it will do? It will invert. So this 0 will be inverted and it will get 1, converted to 1. Now again 0 will come, it will again get converted to 0. It will act as an inverter. Again 1 is given, So 1 will act as a buffer. So this 0 will be 0. You understood this point? See, first of all, what we have at the output, we have reference at 0. And then if reference is 0, then we are giving 1. So at 1, it is acting as a buffer. So output will be 0 only. Okay? Because no change in the output. Then 0 is given. When 0 is given, it will act as an inverter. So output will change from 0 to 1. Okay. Again, next is 0. Again in 0, it will act as an inverter. So output will change from 1 to 0. Why? Because here in the circuit, we see the output is already given as one of the input. And this is the control input. Depending upon this as 1 or 0, this will change. Output will change. So the output is 1, it becomes 0. Now again, 1 is given over here. So whatever will be the input over here, it will represent as the same output. So the previous output is only the input. So previously, what is it? Is it here? It is 0 only. So next will be also 0. So this is the basically output of the differential, and differential means pulse phase shift key. This is the basically input of the DPSK. When it will given to the DPSK modulator, it will represent a phase shift corresponding to 0, it will represent pi. Corresponding to 1, it will represent 0. Corresponding to 0, it will represent pi and pi. So output will be like phase shifted signals of sequence pi 0 pi pi. So this would be the answer. So now if you have understood all this thing, let us just summarize the important formulas, understand things. We have already summarized ASK, PSK, FSK in terms of bandwidth, D minimum, and probability of error, as well as the energy and the quadrature null effect. All that point we have seen. Now there are some important point that is also meant there, that is regarding the locus. Write down that for M array FSK, generally for M array FSK, the locus is circle. For M array, I can show you how PSK, the locus is circle. See, for PSK, for 2 signals, we are having like this. For 4 signal, we will have like this. For 8 signal, the phase difference will be like 45 degree. Okay, and D minimum will be always EB, root over EB, not D minimum distance between the origin. So this is the, like, it will form a circle. As we will increase M, it will form the circles. Therefore, for M array PSK, the locus is circle. For M array FSK, the locus is circle. For M array ASK, the locus is a straight line. The locus is a straight line. Okay. This is some point related to locus. Then there is another important point which is related to minimum shift keying, MSK. Just whenever you see MSK, just you remember that MSK is nothing but is almost similar to FSK. You can just thought MSK as FSK and you can solve the question. Okay. So in FSK we have what? We have FH for orthogonality. We have FH minus FL is equal to RB, NRB. This was that. And for like coherent detector or coherent modulator, we have Fs minus Fl is equal to NRB by 2. So for minimum shift keying, FSK with n equal to 1. If n equal to 1, FSK is known as the minimum shift keying. This is the minimum shift keying condition. For minimum shift keying, n should be minimum, that is, it should be 1. So the relation between FH and FL will become RB by 2. So FH minus FL is equal to RB by 2, and if this is the condition, FSK will become MSK, or FSK is known as MSK. That is, frequency shift keying is known as the minimum shift keying. So this is all with respect to the digital communication, and we will end here only. There are the other topics such as entropy and all that we will not cover because that is not so important from like what I can like expect. So this is the important point from the digital modulation technique, that is ASK, PSK, FSK, we have already covered. So that is all with this video. Thank you.